Welcome everyone to the second day of the first Asian Symposium on Cellular Automaton Technology. Today we have 2 invited talks and 5 contributory talks. Our first talk is by Professor Kenichi Morita, and the session will be chaired by Professor Shomi Roy, who is the head of the Department of Computer Science and Engineering, National Institute of Technical Teachers Training and Research, Kolkata, and Sukarna Mukherjee, Institute of Engineering and Management, Salt Lake, Kolkata. So I invite the session chairs to start today's session.
Thank you, Kamalika. So today in our session, the first talk is the invited talk, and that will be conducted by our renowned Professor Kenichi Morita. So his topic is computing in a simple, reversible, and conservative cellular automata. So let us introduce Sir. Professor Kenichi Morita is a Professor Emeritus of Hiroshima University. He received a PhD in engineering from Osaka University in 1978, and he was a professor of the Graduate School of Engineering, Hiroshima University. He is the leading scientist in the research of automata theory, cellular automata, reversible computing, and formal language theory. Professor Morita is renowned for his work on two-dimensional language accepting automata, complexity of Turing machines, universality of cellular automata, regular and context-free array grammars, and undecidability. He has introduced the concept of partitioned cellular automata in the domain of cellular automata. He has authored more than 100 articles. His high-impact works include findings of parallel generation and parsing of array languages by means of reversible automata, construction of reversible automaton from Friedrich Getz, solving a firing square synchronization problem in reversible cellular automata, self-reproduction in reversible cellular spaces, universal reversible two-counter machines, solution of non-deterministic polynomial NP problems in hyperbolic cellular automata, reversible P systems, a new universal reversible logic element with memory, and reversible in asynchronous cellular automata. As a tribute to Kenichi Morita's ideas and achievements in theoretical computer science, reversibility, and computationally universal mathematical machines, his colleagues, collaborators, and students and friends presented over 20 essays on the occasion of his 70th birthday, which is published as the Book of Reversibility and Universality, an indispensable book for computer scientists and mathematicians, physicists, and engineers. So, thank you, sir. Actually, we are eager to hear from you. So, what do you say?
Thank you for your introduction. At first, I would express my thanks to the organizers of this workshop. I'm very happy to give a talk here. Okay. Today's topic is about simple, reversible, and conservative cellular automaton, in which reversible computer can be implemented very simply. Okay. Reversibility is one of the fundamental microscopic laws in physics. We discuss how reversible computers are realized using a reversible microscopic law of evolution. Here, a new model of a reversible elementary square partitioned CA, ESPCA in short, is used for this purpose. It has the following very simple local function here. And reversible Turing machines are constructed in this cellular space in a systematic way. in this method. In the lowest level, level 1, there is a reversible microscopic law of evolution. In the second level, of evolution, useful phenomena in the reversible cellular space is investigated. In the third level, a reversible logic element with memory, RLEM in short, is constructed using such useful phenomena. In the level 4, functional modules composed of RLEMs is designed. And finally, in the top level, reversible Turing machines are constructed, assembling these modules systematically. First, I focus on the level 1, reversible microscopic law of evolution described by Cellular Automaton. Here we use a square partitioned CA, ESPCA. Here each square cell is divided into 4 parts like this. And each local transition rule is like this. Each cell is has 4 parts, top part, right part, bottom, left. And depending on these adjacent parts of the adjacent cells, next state of each cell is determined. Therefore, local function small f is defined by a set of local transition rules. And global function large F is obtained by applying the local function f, small f, to all the cells in parallel. As we shall see later, it is a very useful framework for giving reversible CA. In ESPCA, a special subclass is called an elementary square partitioned CA, ESPCA. It is rotation symmetric, that is isotropic, and each part of a cell has only 2 states, like these figures. By above, a local function of an ESPCA is described by only 6 local transition rules, like this. For example, a local function of an ESPCA with a hexadecimal identification number 01CAEF is like this. Each right-hand side, a dot pattern of each right-hand side is read as a binary number, and they are expressed as a hexadecimal number. By such a notation, we have 01CAEF for this cellular automaton. Now, reversibility of an ESPCA is defined as follows. It is reversible if large F is injective. It is known that the global function f, large F of an ESPCA is injective if and only if its local function f, small f is injective. Therefore, PCA, partitioned cellular automaton framework, is very useful for designing reversible cellular automaton. that is, to obtain a reversible CA, it is sufficient to give a PCA whose local function is injective. Here, we consider focus on a particular ESPCA 01CAEF. This one. It is denoted by a P0 hereafter, since 01CAEF is slightly long. P0 is reversible, since there is no pair of local transition rules with the same right-hand size. Okay. A space moving pattern, in particular, called glider, exists in P0, and it shows interesting behavior. Then we investigate the cellular space and try to find useful phenomena in this reversible cellular space. There are three useful small patterns in P0. The first one is a blinker. This is a periodic pattern. Okay. It has a period 2. Okay. Second is a block. It is a stable pattern. However, a block is used only for writing comments. Hence, it has no functional role. The third one, glider, is the most important pattern. It has a period of 12, and it moves one square diagonally. Okay, and therefore it is used as a signal in the following sections. By the way, to follow evolution process of patterns in P0 is very complicated, and it is very hard to follow by paper and pencil. Therefore, we use Gori, which is a free software for simulating cellular automata, for simulating ESPCA P0, since evolution processes in P0 is generally very complex. Now I show some example. Okay. This is Gori. You can see blinkers and a glider. Okay, blinker is a periodic pattern of period 2, and glider is a space moving pattern. Okay, like this. Okay. We also use a block, but it is used only for writing comments. Therefore, it is a stable pattern. Okay. To find space moving patterns or periodic pattern is relatively easy, since this cellular space is reversible and conservative. In particular, number of particles is conserved throughout its evolution process. Therefore, if we start from such a random-like pattern, we can always find space moving patterns and or periodic patterns. How this pattern evolves, okay? You can see many space moving patterns appear and fly, okay? Okay, around the center of this configuration, various periodic patterns appear. Therefore, it is easy to find various space-moving patterns, but it is not so easy to find useful phenomena. To find such useful phenomena, we have to make various experiments to collide a space-moving pattern with a periodic patterns. Here we found 3 useful phenomena in P0. Interacting a glider, this one, with a blinker, this one, we obtain 3 useful phenomena, though their evolution processes are complex. First one is right turn phenomena, or a phenomenon of a glider. By colliding a glider with this blinker, a glider finally turns rightward. Okay, but it takes more than 300 steps, and intermediate evolution process is rather complicated. Anyway, this phenomena is used to control the movement of a glider. The second is a U-turn phenomenon of a glider. By giving a glider and collide it with a blinker, this glider makes a U-turn. It is used to test whether a blinker exists or not. And it is also used to reversibly merge signal paths. On this point, I will explain later. The third phenomenon is shifting a blinker by a glider. By colliding a glider with a blinker in this way, the glider turns rightward. At the same time, blinker shifts leftward by 6 cells like this. It is used to realize a 1-bit memory, and memory state is kept by the blinker position. It is also used to test whether a blinker exists and to reversibly merge signal paths. But note that this process takes more than 2,000 steps. Therefore, intermediate evolution process is very complex. But anyway, finally, such collision makes a blinker shift. Okay. I will show it using Gori. Sorry. there are many blinkers and one glider like this. And glider glide with a blinker. And in this case, it makes a right turn. Here, blinker is shifted leftward, but it takes more than 2,000 steps. It takes a bit time. Okay. Anyway, it is this blinker is shifted. Right turn, again right turn, and right turn, U-turn, and shift the blinker like this. In this way, glider can shift and glider's movement is controlled by placing blinkers appropriately. In the third level, we construct a reversible logic element with memory Rem in this cellular space. Rem, in short, is a kind of reversible finite automaton having output ports as well as input ports. Here we use Rms rather than a reversible logic gate as a logical primitive because reversible Turing machines are easily constructed out of it. As we shall see, some Rms can be implemented using only the three phenomena in P0. This and this. These three phenomena, using them, we can implement some Rms. Okay. Here we represent each Rm in these figures. Okay. Take an example, Rem 431. Here, 4 stands for 4 input and 4 output element, and 31 is a serial number in the class of 4 IO element. Okay. Dotted and solid lines show the relation between input and output. Here, A, B, C, and D are input ports, and W, X, Y, Z are output ports. Okay. If a signal goes through a dotted line, then the state does not change like this. On the other hand, if a signal goes through a solid line, then the state changes like this. Okay, if this particle or signal goes through a solid line, then the state becomes 0 from state 1. Okay. An Rem R is called universal if any Rem can be simulated by a circuit composed only of R. It is known that every two-state Rem with 3 or more I/O ports is universal, like this. Therefore, Rem 431 with 4 I/O ports is universal. Therefore, we use this element to compose reversible Turing machines. But at first, we consider a simple RM22 and try to construct it in ESPCA P0. RM22 is an element like denoted by this figure. Although RM22 is non-universal, RM22 is here, and it is non-universal. However, it is simulated in ESPCA P0 very easily, and therefore it's useful to understand how it is implemented in P0. Here, only two phenomena are used: right turn and shifting blinker. No, not a thing. Shifting blinker. Okay. This is a pattern that simulates RM22 in P0 cellular space. The blinker near the center here is a position marker to keep 0 or 1. Small circles, two circles here and here, indicate possible positions of a marker. If the position marker blinker is to the left side, then we assume this element is in the state 0. Okay. If the blinker is right in the right circle, then it is in the state 1. Okay. And input signal given to the input port A or B. Okay. First, we consider the case state is 0 and the input is B. Then the coming signal glider goes along this path. Okay. At a point P, it interacts with the position marker, and by this position marker is shifted to the right. Namely, the state is changes from 0 to 1. And finally, the glider goes out from the output port X. If in the state 0, glider is given, to the input port A, then it goes along this path, and therefore it does not interact with the position marker. Here, these two paths in this case and this case are merged at the point P, and in both these cases, output is given to the port X. Therefore, at the point P, the path is merged. This is a reversible merge. Other cases are similar. Therefore, anyway, this pattern realizes the two element correctly. Okay, I show how it is simulated in this cellular space. Okay. Here, position marker is placed at this position. Therefore, this element is in the state 0. And glider is given to the input A. Okay. In this case, glider does not interact with the position marker and goes out from the port X. Okay. Next, from the glider is given to the port B, and the state is changed from 0 to 1. Okay, it moves cyclically. Okay, like this. Okay. The pattern that simulates RM431 is a little bit complex. Therefore, I skip the explanation, detailed explanation. However, 3 position markers are used to keep states 0 and 1. And this is because we need several access paths to know the state, because there are 8 cases of operations. Therefore, we should know the state and which input is given for each case. This is 431 simulated in this cellular space. There are 3 position markers colored in blue. Okay, here 3 position markers are shifted synchronously. By this, the state is changed from 0 to 1, and so on. Anyway, by this configuration pattern, RM431 is correctly simulated. In the level 4 and level 5, we construct reversible Turing machines by using RM431. The Turing machine is defined in this way, but I skip this formal definition. The important point is that Turing machine is defined by a set of quintuples, okay? Q, S, S prime, D, and Q prime. Here, Q is a present state and S is a red symbol. If the machine reads S in the state Q, then symbol is rewritten into S prime, and head is shifted to the direction D, and it becomes the state Q prime. A reversible Turing machine is defined as follows. For any pair of distinct quintuples, this and this, if the next states Q1 and Q2 are the same, then the written symbols S1 prime and S2 prime are different, and shift directions D1 and D2 are the same. If such condition is satisfied for all pair of all the pair of the Turing machine, then it is called reversible. It is known that for any irreversible Turing machine, we can construct a garbage-less reversible Turing machine that simulates the former. It is a classical result by Bennett. We consider two simple examples of Rtms. First example is T parity. It is defined by these 5 quintuples. It is very simple. It reads input strings where unary number n is given to the input tape like this. Okay, and if the unary number is even, then it accepts the input. Otherwise, reject it. Okay, and all the red symbols are complemented. The second RTM example is T power that accepts the strings 1 to the 2 to the case. Okay, namely, it accepts unary number which is a power of 2. To construct these reversible Turing machines, we prepare some two kinds of modules for constructing them. First one is a tape cell module composed of RM431. It is a circuit that simulates 1 tape square of an RTM, reversible Turing machine. However, today I skip its detailed explanation. Another module is a state module. It is a circuit that simulates 1 state of an reversible Turing machine. By assembling state modules in the left side of this figure and attaching a tape module, tape unit that is composed of a tape cell module, we can compose any reversible Turing machine using RM431. And by putting this pattern that simulates RM431 in P0 as a corresponding place, we can construct a configuration in ESPCA P0 that simulates T parity or T power like this. On the left-hand side, there is a finite state control of each reversible Turing machine. And to the right, a tape unit is attached. Oh, I show how reversible Turing machine can be implemented in this cellular space P0. Okay? Basically, this Turing machine is composed of blinkers, blue objects and yellow objects, and giving a single single glider to a start port, it starts to compute. And purple colored cells indicate block. They are only used to indicate comments. Therefore, essentially, this Turing machine is composed only of blinkers, these blue and yellow objects. Okay. However, from these blinkers, RM431 is composed here or here, and by assembling these RMs, state modules for Q0, Q1, Q2, and so on are constructed. And here is a tape unit. And the tape unit composed of an infinite copy of tape cell module. And each tape cell module is further composed of 9 RM431. Okay. And therefore, all the body of this Turing machine is composed only of blinkers. And by giving a single signal to the start port here, computation starts. Okay. This signal is processed at each RM431. 431. This is a reversible Turing machine that accepts unary numbers of length of power of 2. Okay. Here, input is input n is 4, but it takes very much time. About 75 million steps. Therefore, we should use a hyperspeed mode. We accelerate the evolution steps to 8 to the 7th, okay? But if we accelerate, signal moves very fast. Therefore, it is very difficult to see the signal. Finally, the signal goes out from the accept port here. But to check the answer, to record the answer, we put here blinker. At first, it is at the position, a neutral position. if it is accepted, then it is shifted to the right. But it is rejected, then it is shifted to the left. Okay, I will continue the computation. Here, time step is indicated. 40 million. We stop. It is already accepted, but please wait a while. Oh, here is a glider. Okay. Glider moves here and goes through the accept port. Here, therefore, we can recognize the input is accepted. And finally, this switches this blinker to the direction of accept. Okay. In this way, computation is performed in this cellular space. We saw that even from a very simple reversible microscopic law, reversible computers Rtms are realized in this construction method. In particular, 3 operations, which are right turn, U-turn of a glider, and shifting a blinker in the reversible CA are sufficient to be computationally universal. In this construction, Rtms, reversible logic element with memory rather than reversible logic gates, greatly simplify the construction of reversible Turing machines. It is left for the future study to find still simpler reversible CS or frameworks in which reversible computers are realized. That's all of my talk. Thank you for your attention.
Thank you, sir, for your wonderful talk. So now it's an open session. So the participants are requested to ask the questions.
Actually, I want to ask one question. Hello, sir.
Yeah.
My name is Shubhri.
Pardon? Pardon, I can't hear.
Please.
Hello, sir. Actually, you said that from level 0 in cellular automata, when you are adding memory, and then you get at the highest level, you are getting the reversible Turing machine. So is it possible that if suppose I want to see some C as universally computable, then is it possible to prove it without adding any memory?
Pardon, without, sorry,
with adding memory, we can get a reversible Turing machine. So suppose I want to prove some cellular automata which is universally computable. Is it possible to do that without adding any memory? Or rather, I can ask that if we do not add any memory, then up to which level we can go?
Here we used a specific logic element called Rem. But there are, of course, other way to prove universality of cellular space, in which, for example, reversible Turing machines or reversible counter machines can be implemented. Therefore, other logical module or relatively classical module like reversible logic gates can be helpful for proving universality of cellular automaton. But here I used reversible logic element with memory Rem because I thought it helps to simplify the whole construction of reversible Turing machine. But of course, it is not the only way. We should investigate, of course, other way, because several other way may be much better than this method.
Okay. Thank you, sir. Yeah. Thank you, sir. Thank you so much.
Okay. Thank you.
Any more question?
Yeah, I have one question. Yeah, thank you, Professor Morita. Amazing, you know. My question is, how far you are from developing a general purpose computer architecture architecture with this construction?
Sorry, I could not hear you well.
Can we construct general purpose computer architecture or general purpose computer using this construction?
Yes, it is of course possible. Yeah, because it will becomes much more complemented. But I think it is possible. More realistic computer can be constructed using these logic element or in this cellular space. But one problem is that in my construction so far use only one signal in the system. Therefore, in order to speed up or making computers more efficiently, some kind of parallel mechanism will be needed. But in the reversible space, parallelism is relatively hard to manage. Therefore, it should be investigated in the future. Okay?
Yeah, okay. Do you have any plan of doing so?
Yeah, of course, I want to design such a computer, but as I have just said, there need some further investigations to overcome some drawbacks. Okay, Therefore, at first, I want to investigate further basic investigations to realize such a computer. Okay.
Yeah, thank you, Professor Morita. Thank you.
Any more question?
Shukarnandi, Professor Gennaro raised hand.
Okay.
Hi, Kenichi. Good night.
Oh, good night. Okay. Good night or evening.
It's very nice to see you again. And thank you for your very interesting talk.
Thank you.
My question is mainly on the gliders and oscillators that emerge in this cellular automaton. Can you reproduce these oscillators and gliders from collisions?
Reproduce. Of course, some phenomena.
That is the problem about self-organization.
Reproduction or self-organization. Okay.
Yes.
So far, in this cellular space, I have not yet found such kind of useful phenomena. It is, of course, left for the future study. Yeah. But in this cellular space, because number of particles is conserved. Therefore, it often occurs. The original patterns occurs repeatedly. For example, if we collide a glider to this blinker, it shows a very complex evolution process. But finally, it produces one blinker and a glider. Therefore, there is a possibility to make a glider or some other pattern by colliding glider and other oscillators. Therefore, it is worth studying to find such phenomena. Yeah, but so far I have not found such a kind of phenomena. Yeah.
Okay. In the same direction, you see some glider gone in this automaton?
Not yet. Not
okay.
Yet. Yeah. A glider, in the narrow sense, glider gun cannot exist because it is conservative. Therefore, number of gliders cannot grow indefinitely.
Oh, yes, you are right. Okay. So thank you very much, Kenichi.
You are welcome.
Kamolika?
Yes. Sir, I have a couple of questions.
Yeah.
So first, it was amazing. It was like I was just listening to you and I was amazed what you are doing. Okay, sir, you are taking reversible cellular space. So do you think that only reversible cellular space will be useful for developing such kind of universal computation like Turing machine or other universal models of computation, or can irreversible CAs can also be useful?
Of course, irreversible cellular automata and irreversible models are also interesting. But so far, I have been mainly studying reversible computers. But I found, in spite of the constraint of a strong constraint of reversibility, its computing capability does not decrease. And furthermore, by using some time symmetric nature of reversible systems and reversible cellular automata, construction of machines can be simplified. It is not very intuitive, but I found such constraint of reversibility helps to construct reversible machines in some case. Therefore, I am now concentrated in studying such problems. But of course, I think irreversible systems may also have very interesting aspects of computing and construction. Okay.
Okay, sir. And can we get any other way of sending the signals apart from these blinkers and gliders? Or is these are the only ways? What is your position in that?
Blinker and gliders used here is only for this model of cellular automaton. Of course, for this cellular automaton, blinkers, assuming this specific local transition rules, I found blinkers and gliders are very useful. But for other cellular automaton that obeys other local transition rules may have different features. There other objects will be useful. And of course, space-moving patterns like gliders will be useful in other models. But its property will be very different. Therefore, we should investigate these properties one by one. Unfortunately, we should investigate the properties for each model of cellular automaton. But the key point is to find some glider-like object to propagate the signal, and some stable or periodic pattern for constructing stable structure of a computer. At least two kinds of such objects are needed. But concrete shape of these patterns are different. Therefore, we should investigate for each model. Okay.
Sir, please. Sir, my third question is, so you are telling that if you change the type of CA and type of rule, so we might be getting some different kind of patterns which might be useful as this glider or this stable block. So can you do you think that some other type of CAs, like apart from the partition CAs, are also good candidates to be reversible Turing machines?
Yeah, of course. Other than other CA, besides partitioned cellular automaton, will be very important to investigate. And of course, various results on computational universality on reversible CA other than PCA have been derived. But practically, partitioned cellular automaton framework is relatively useful for designing reversible CA. Therefore, I have been mainly used this model. But of course, other method should be investigated in the future, of course. Is it can be the answer for your question?
Yes. Okay. And the last query is: are we going beyond stored program architecture by doing this, or we are still stuck with that architecture only?
Well, pardon, what architecture?
Are we going beyond stored program architecture?
Yeah.
If you are thinking of planning for general purpose computer, will we be following, will you be following the stored program architecture, or it will be going beyond stored program architecture?
Yeah, so my study so far done is stored program architecture. But of course, I am interested in beyond stored program architecture. But I have not yet done it. Okay. Only I am interested in, but I have not yet made an approach to it.
Okay, so you think that it is possible. Okay. And I am very much interested to see the outcome of it. Okay, thank you so much.
Some direction maybe I hope some direction may open for such investigation. But so far, I have not. I do not have a very good idea for that. Yeah.
Okay. Thank you, sir.
Okay. Any more question?
So, small question.
Yeah.
So, do you ever see the partition?
There is some echo.
Do you ever see the effect of partition in this microscopic local rule? So that's we use any kind of partition in this.
Sorry, I cannot hear well. Some howling is occurring.
One is on the speaker, I think, at the same room.
So my question is that if we add any kind of partition in these local rules, any kind of partition, any kind of asynchronism in these local rules, do you ever seen the effect of partition, how sensitive these local rules with the effect of any kind of partition?
Perturbation or some kind of asynchronism will be, of course, a very important problem to practically realizing such system. Also, for that problem, I have not fully investigated. However, reversible logic element with memory, Rtm, has some asynchronous feature because input signal can be given at any point time. But in the case of reversible logic gate, 2 or more input signals should given exactly at the same time. This is a very different feature of Rtm. Of course, in my reversible cellular automaton, signal or update of states is strictly synchronous. There is no asynchronism, but in the level of reversible logic element with memory, Rtm level, some kind of asynchronism is allowed. At any time, input can be given. Therefore, such a feature will make some help for practically implementing a system. But so far, I have not yet fully investigated this problem. Is it okay?
Thank you very much. And thank you very much for this talk also.
Thank you.
Thank you, sir. So any more questions from the audience side? Sir, I have a question. Actually, as you are actually interested in designing of general purpose computer, so if we think about the parallel processors like MIMD architecture, we use the interconnection network in that case. And for designing the interconnection network, we use cube network, omega network, delta network. So using this, the way you have shown us, so can we implement such type of networks?
Sorry, I could not hear well the
Yes.
last sentence.
Yes, sir. Actually, I'm asking, my query is actually on the interconnection network. So when we think about distributed or parallel processing architecture, we use omega network, delta network, cube network for the interconnection purpose. So can we implement such type of things using this scheme?
Also, on such a problem, I have not fully investigated, but each part of such system can be built in the method I have shown, but interconnecting structure or communicating several parts should be designed in some other technique. In reversible computing, communicating with some delays, or in particular, waiting. Waiting is very difficult in reversible system. Therefore, such problem, waiting a signal for some time should be handled in some irreversible way. Therefore, in such as a total system, reversible part and irreversible part of, for example, for communication is mixed. Some hybrid architecture will be practically useful, but such a system should be more investigated in the future. But okay.
Thank you, sir. So, any more question? Okay. So we are ending the session now, and there will be the break. So I hope we will be back by 11. So thank you, Professor Morita, again for your wonderful session, and thank you, the audience.